I want to explore this more. I want to talk about binary search trees. So it would be neat if we could make a tree that would be in this shape like this, right? But the tree we wrote doesn't do that. So maybe what we could do is we could take our binary tree.cpp, rename it, let's call it tree set. Let's make a set of ints stored in a binary search tree like this. And we're going to have basically the same code, but I'm just going to rename it from binary tree to tree set. So I've actually done that. I took the liberty of doing that before class. So I've got this new project with treeset.h, treeset.cpp. And treeset.h, I mean, the code should look pretty similar, except it has some methods here that we're going to now write. So, for example, look what it has. Print, contains, print sideways. We wrote those last time. So I just copied those over. And I've added blank headings for some more methods that I want us to add to this thing. What can you do with a set in the library, the Stanford library? You can add things, remove things, and search it. That's the main stuff you could do with a set. I want to make a class of R's that we could do those same operations. OK, let's talk about add for a second. One thing I kind of waved my hands about and didn't spend very much time on last lecture was how to build the tree. The way that we built the tree, the way that we added stuff to the tree before, was we actually just in the client program, the main method or whatever, we just made a bunch of pointers and just manually glued the tree together and then handed that off to the binary tree class. Here, use this as your root. And we just built it all with the pointers from scratch out in the client. We did not do this when we used the Stanford set class or whatever. We didn't wire together a bunch of nodes and hand them to a set. That's clunky. What I want is, as a user of this thing, I really want it to just have an add method. And I give it a value, and it'll put it in the tree somehow for me, right? That's what it should do. So that's kind of what I want to morph this code into doing. So if you make a tree set, you're saying, remember now, we are thinking about this in two ways now. This is a binary tree. We've been learning about trees and pointers and nodes and left and right and recursion and all that stuff. We're going to think about it that way. But that is an internal view of how this is being implemented. But now we also have to think about this. We're building a data structure, and there's going to be some other piece of code like main that's going to use this structure. And they don't give a shit about nodes and pointers and left and right and recursion. They just say, here, add this. I don't care. Whatever you got to do, just put it in there somehow. And then if I go searching for it later, I want to find it. Right? They do not care about pointers and left, right, recursion stuff. Right? So we have to think about this in those two ways, as the implementer and as the client. We've already used treeset as a client. We called it set from the Stanford library. So now we learn about it in the other view. So if you're making a tree, initially the set contains no data inside, right? It's empty. So if I were going to implement the treeset constructor, remember that the treeset has a private member variable for the root of the tree, right? What should the root be when I first construct the tree? There's no data in here, so it's null, right? So root is null. OK, now if you want to add a value to the tree, if we're going to write this piece of code right here, this might seem like a really simple thing to do. Well, the root's null, so I'll just set the root to be a new tree node that stores that value. That would be fine. So it goes from empty to storing that node. But that doesn't work for the general case, right? You have to imagine that maybe your set has a bunch of already existing elements, and we have to go put this one in with them, right? That's what I really want to be able to do. So let's talk about that. Let's talk about how you would add an element to a binary search tree. So how would you do it? Pretend, I mean, we don't have the code set up to do this yet, but pretend somehow we've built this. This is our tree. And it's a BST. It's a valid binary search tree. And then they say add 3. How do we add 3 to this? What's the English kind of algorithm for what we should do? It matters where we put it, right? So we want to still be a binary search tree when we're done. So what would you do? Yes, sir.
We want to recursively walk down the tree, and if the value we're adding is greater than the current node, then we'll go to the right. If it's less, we'll go to the left until we reach a null. And then we go back one and add the filter to the next place.
Yeah, he's right. It's the same as the idea we just talked about for searching for contains. If we're adding something that's smaller than where we are right now, go left. If we're adding something bigger than where we are right now, go right. Eventually, we get to the bottom. We get to the empty, the null, the place where it should go, and put it there. That's the idea. Yeah. So let's try to write that. Let's try to write that. So I'm going to open up my tree set, and add shouldn't do this. Now, when you say go left and go right, how do I go places here? How do I go to a part of the tree? What do you mean by that? I mean, I'm adding a value. I just need to go somewhere, yeah?
If you need a helper that takes the node in.
Yeah, just like all the other methods, we need to make a helper that tells me where am I in the tree, what pointer, what part of the tree, what node am I at right now. So yes. Let's make a helper in my H. Remember that for every public method that the client can call, we'll write a private version of the same method that we can call. So let's do void add that takes a tree node of what node I'm at and the same int value that we're trying to add to the tree. Right? So now back here in the CPP file, we've got this, and we're going to write add root comma value, right? And so that's going to be void tree set add that takes the node and the value. OK. I like what you said, go left, go right, depending which, where we're going to add this thing. But this is usually recursive, right? Trees are recursive. So when you do recursion, you think about base cases. What are some base cases here? Null, like maybe if the node I'm at is null. OK, I'm not sure what to do in that case. Let me come back to that. Let's do that next. But maybe if it's not null, then it's some kind of node, and it has children trees and stuff like that. So maybe this else is honestly the recursion part might be kind of easier than the base case for a second, because you described what to do. If I'm not the right place to put it, I need to go left or right or something like that. Maybe if the value I'm adding is less than this node's data, what should I do? My node stores 12, and I'm adding a 6. What should I do? Go left, right? I should go to the left. So you might say node left equals something, but I think what that really means is I should call add, and I should pass node left, and then this same value. OK? So then how about else if the value I'm adding is greater than the data of this node, go to the right? Yeah? You have a question? Yeah?
It work at the end, right? Because if you get to the point where node equals null, you lost your pointer kind of to where you're going to drop it off. Right?
Are you saying I've written bad code?
Yeah.
I think you're a very judgmental person. But you're totally right. Yeah, she's saying, I think she's concerned that we're falling into what will be perhaps a boogie solution. And you're right. And I want to do that for a second. I want to fall in the pit, and then I want to climb out. So let's do that, and then maybe you can tell me how to climb out. There's one more case I haven't considered, which is I'm not less than the data to be added, or the value's not less and the value's not greater. The value is equal to this node's data. So they're adding a 12, and I am a node that stores a 12. What should I do in that case? What does that mean? Yes?
Do nothing.
That means I don't need to do anything because this is a duplicate thing. They're adding a number that is already in the tree, right? So here, that means duplicate, do nothing. So in fact, I don't even need to say else. I just wanted to write that out so you could think about the fact that that is a case. And we don't have to do anything for that case. OK, so what's going to happen is we're going to be going left. We're going to be going right. Eventually, we get to the place where the node should be, and it's null. And so I think what almost every student wants to do here is mostly right, which is you say, let me get my picture back on screen. You say, if I'm adding what, 3? Then I think what happens is it's smaller than an 8, so you go left. It's smaller than a 5, so you go left. It's bigger than a 2, so you go right. It's smaller than a 4, so you go left. And that sets me to a null place. And you say, aha, right here. I want to change that null. Instead of being null, make it be an arrow to the new box, right? And so a very natural thing that most students want to write here is, if node is null, then change node to point to this new box instead. So they say, well, if it's null, make it be a new tree node that stores this value that they're adding, right? Looks great. This is so close to working, but it totally doesn't work at all. She's right. She's super judgy, but she's right. I hate when students are right. It makes things less fun. I'm just kidding. Grading mentality seeped in there. So, OK, why doesn't this work? I want to talk about this. Let me prove to you that it doesn't work. Let me show you that it doesn't work. So if I open up this client, the client isn't really a very important program. It just makes a tree, adds things to it, and then it calls print, which print is the same print that we wrote. I just copied it over. So if our thing is actually adding the nodes, this should print the nodes out, right, that it added. So I'm going to compile this and run it, and nothing gets printed. And what's happening is nothing got added. At the end of all those calls, the tree is still totally null. That's weird, isn't it? didn't seem to add anything. I really thought we were onto something here. I blame you guys. You helped me write this. Well, it's kind of my fault. I didn't listen to you. So why doesn't this work? I want to talk about why this doesn't work. And it's hard to understand, which we're going to do more with this on Wednesday as well. But why doesn't this work? Well, wait. Here. This is what we wrote. We wrote this almost letter for letter, basically. Why doesn't it work? Well, here's a tree. We get all the way down to the point where node is pointing at this one. Or what am I adding? Let's say I'm adding 31. Value's 31. Okay? Node is pointing at this 42. And I walk through the code. I say it's not null, but the data in this node is bigger than the value that I'm adding, so I need to go to the left. So I say add node left. So node left is this pointer, which points to nothing. So now I call it with node set to null, right? Okay, so now the flawed understanding is I think people think that node is like pointing to here, but it's not. If node is null, that means node is pointing to nowhere. Node is pointing at nothing. Node is not pointing to any part of this tree anymore. Node is just some external little pointer that points nowhere now. It doesn't point to this thing, it points to nothing. If I set node to null, that doesn't mean point at this. So now I say, oh, node is null, make it point to a new tree node. Okay, hooray, make a new tree node that has a 31 inside. Yay, here I am, everybody. Now I'm part of your tree. Hey, how come no one will play with me? Oh. Nobody attached the thing to the 42. It looks like it did right here, but I hope you understand. This is really similar to that James Bond shit I was talking about with linked list. Do you remember that? How do you change a linked list? What's the trick? You have to be like back by one and reach ahead to detach the train cars or whatever. So that same kind of thing is happening here. We went too far, and now we can't add the thing to the tree properly. In the linked list, I know it's about time for me to wrap up, but in the linked list, the way we fixed it was by stopping one early. There's a really cool fix for the same issue here that's simpler. It's a single character. Fixes the whole thing. And that character is, if you put an ampersand after your pointer, then node really does point to that little null box right here. Not a copy of it, but really points to it. And changing node does change it. And this little ampersand makes this entire thing work. And I think it's hard to see why, so that's where we'll resume Wednesday. We'll understand it better.